Can anyone respond to me?
Good morning, sir.
Good morning.
Good morning, sir.
Fine. Then we'll go ahead with this particular class. In the previous class, we have studied about different parts of VLSI and different types of MOSFET and how the MOSFETs have been designed and what are the symbols of the MOSFET. And now, in this particular class, we will be studying about fabrication methods of how that particular device or integrated circuit is being fabricated. Okay, let us start this session or class with MOS fabrication. MOS fabrication process. So now, what is meant by fabrication first of all? If I talk about fabrication simply, if I want to define it a very easiest way, fabrication is nothing else but it is manufacturing of any kind of structure or shapes of different material from the raw material. If you want to manufacture any kind of structure from raw material, that kind of process we call it as a fabrication. So now here in this particular fabrication, we might have heard about different aluminum fabrication or else different metal fabrication. That is nothing else but if they take one kind of metal and they try to manufacture a kind of substance or structure from the raw material. In the same way here, regarding our VLSI fabrication, MOS fabrication is nothing else but we'll be taking silicon as a raw material and will convert that raw material into integrated circuit. So that's why the name has been come here as a fabrication process. So it's a method or it's a way of manufacturing integrated circuit from the raw material, which is nothing else, silicon. So now here, MOS fabrications are the types of MOS fabrications. Types of MOS fabrication. The first one is called as an NMOS fabrication. Second one is called as an pMos fabrication. Third one is called as an CMOS fabrication. Fourth one is called as a bicmos fabrication. Bicmos fabrication. So these are the four different kinds of fabrication which we will be studying as per our course. The first one is an N type of MOSFET fabrication. Second one is called as an P-channel MOSFET fabrication. Third one is nothing else but it's a sandwich of these two. That is nothing else but pMos and NMOS is nothing else but CMOS. So it's a CMOS fabrication. And the fourth one is a bicmos, which is being formed by using CMOS technology and the BJT technology. So now let us see one after the another, and hopefully this entire class will be completely dedicated to this kind of fabrication called as an NMOS fabrication. And I request everyone to kindly concentrate in the NMOS fabrication. Why? Because the NMOS fabrication method is very much similar to the pMos fabrication with respect to only the difference is that the kind of charge carriers will be changing. Only that's the difference. So if you can understand and if you can reproduce this all the steps one after the another, then pMos will be very much easier for you to understand this kind of fabrication. So let us see now what is meant by NMOS fabrication. Basic steps involved in MOS fabrication. Generally, any kind of MOS fabrication will be having nearly some approximately 10 steps of patterning the layers. So there will be, in general, there will be 10 steps in order to manufacture or in order to get a physical integrated circuit. So now, among those 10 steps, there are few kinds of steps which will be always on repetition process. So it will be repeating every time. So these three steps are very important. So these three steps will be always repeating throughout the process of fabrication. The first step is nothing else but it is called as a create. First step is called as a create, and second step it is called as a define, and third step is called as an etch. So these are the three main steps. These are the three main steps which will be always repeating throughout the process of fabrication. So what actually happens in the create? If you talk about create, here in the first step of create, we'll be creating different kinds of layers upon the silicon, and the creation of these different kinds of layers will be on the silicon and also inside the silicon. If I talk about on the silicon, then there will be basically two types of steps which will be always happening. The first step is called as an deposition of some kind of impurities of some kind of layers onto the wafer, and then deposition, and the next one will be thermal growth. These are the basically two steps which happens on the wafer, on the surface of the wafer. And next one, if I talk about inside the wafer, again there are two kinds of steps. That is nothing else but diffusion of impurities into the wafer, and also ion implantation. So basically, in create, we'll be creating some steps, we'll be creating some layers or patterning some layers onto the wafer and into the wafer. So if it is onto the wafer, if it is on the wafer, then it will be deposition and thermal growth. As we go on with the fabrication, we'll understand what is meant by deposition and thermal growth. The next one, if it is into the wafer, then the two main steps will be like ion implantation and diffusion. These are the two steps which happens in the create process. So create is nothing else but we'll be creating the layers, or we'll be patterning the layers onto the silicon chip. So that is called as a create process. So next one, in define. Define is nothing else but in define a step, or in the define step, it's like I can put it like this. We'll be defining the patterns from the mask. We'll be defining the patterns, or else we'll be deriving the patterns. Patterns are nothing else but these are the geometric shapes, or these are nothing else but electronic data which has to be taken from the mask, and it has to be put upon this surface of the layer or into the wafer by using a process called photolithography. So now here define is nothing else but it is a process where the patterns are defined or derived from mask using photolithography. And here, if I talk about what is meant by mask is nothing else but it's a specification of some geometric shapes which has to be created upon the surface of the wafer. It's like a geometric shape has to be created. What should be the dimensions of each layer, and how to what extent it has to be diffused into the surface or into the wafer. Those are nothing else but the mask definitions. So mask is nothing else but it's a specification which tells about the geometric shapes which are to be patterned onto the surface of onto or into the wafer. Then what is meant by photolithography? photolithography is nothing else but it's also called as like optical lithography, or else the other name is UV lithography, ultraviolet lithography. It's a process of taking or extracting the geometric shapes or geometric data from the mask, and it will put it on the wafer. So it will extract the geometric data from the mask, and it will put it on the wafer. That process we call it as a photolithography. It's basically that happens in the presence of light. So that's why we call it as a photolithography. The next one, etching. Etching is nothing else but simply etching means removal. Etching means removal. Remove. The meaning of etch is remove. So removal means here, see, during the process of making of this integrated circuit, there will be many different kinds of steps where you want to remove some unwanted layers at that particular time. If you want to define the source and drain, then I need to remove some layers from the substrate, and this process of removing the layers, unwanted layers, are called as a etching process. So now throughout the process of fabrication, you will be having these three main steps: create, define, and etch. Create, define, etch are the three main processes which will be happening throughout the process of fabrication. So if I want to draw the flowchart of this one, flowchart of this fabrication, the flowchart will be this way. The flowchart goes on like this. First, you'll be having some silicon wafer. Then that silicon wafer, material formation will be done. Material formation is done by diffusion process, or it can be deposition process, or implantation process. So first you'll be taking some wafer, pure wafer, and that will be converted into some other step by using some material, and that material will be formed by using diffusion or deposition and implantation. The next one, layer patterning is done. Layer patterning is done by photolithography. And after photolithography process, the last process will be etching. It will be etching. Then it goes on to the first step again. So it will be a continuous process. So this is a flowchart for this fabrication, MOS fabrication. First, you'll be taking a pure silicon wafer, and here wafer is nothing else but it's a piece of silicon. The piece of silicon is also called as wafer or die. You can even call it as a die. So then, after that wafer is being then formed into some material, formation has been done by using diffusion, deposition, or ion implantation. And then after ion implantation process, the next will be the photolithography process, where the layer patterning has been done. There is nothing else but data will be extracted from the mask, and it will be put it on the wafers. And after that, last one will be etching process. The unwanted layers will be etched up in order to form another step, in order to move further in the process of fabrication. So this is a flowchart for this fabrication. Now we'll enter into the core part of this fabrication. First one is a NMOS fabrication. I hope this outline of the fabrication is understood by you. Now let us see fabrication. I'll divide this board into 4 parts, so that we are supposed to draw now here nearly 10 different diagrams, how that integrated circuit is being designed. So I'll divide it into 4 parts so that you can understand neatly each and every diagram. First one, the first step. Okay, I'll write it somewhere else. It is NMOS fabrication. NMOS fabrication. So first one, step number one. Step number one is substrate formation. First step is substrate formation. So in the substrate formation, you will be taking the purest form of silicon. You'll be taking the purest form of silicon, and into that particular silicon will be diffusing P type of impurity. See, and now if you want to design or manufacture N type of device or N MOSFET, then the substrate has to be the opposite to that N. That is, P type substrate has to be, you're supposed to create P type of substrates. If you're manufacturing P type of device, then the substrate will be N type of substrate. So now here, since I'm trying to manufacture N type of device with a fabrication process, then my substrate will be P type. So in order to get the P type of substrate, first I'll be taking a purest form of silicon, a part of the purest form of silicon, which is called as a wafer or die, and into that particular die or wafer, I'll be diffusing P type of impurities. P type of impurities. Let the source of P type of impurities be boron. Let me take a boron into consideration, and I'll pass this boron. I'll subject this boron to high temperature, so that at that high temperature, nearly it will be around some 900 degrees Celsius to 1200 degrees Celsius. At this huge temperature, this P type of impurities will be diffused into this purest form of silicon, which is called as a wafer. So now here, I'll take a pure silicon, and I'll diffuse the P type of impurities. I'm not drawing that one. Then it will get converted into P type of substrate. Now, if I talk about the dimensions of this P type of substrate, here the diameter will be, the diameter of this one has to be from 75 mm to 150 mm. 75 mm to 150 mm. Diameter will be from 75 mm to 150 mm. Then about thickness. The thickness of this one will be 0.4 mm. Thickness will be 0.4 mm. And the temperature which is used, temperature will be 900 degrees Celsius to 1200 degrees Celsius. Temperature will be 900 degrees Celsius to 1200 degrees Celsius. So now I have talked about diffusing of the P type of impurities into pure substrate, I told. So now, what will be the concentration of this P type of impurities, or what will be the concentration of impurities? The concentration of impurities into a wafer will be per centimeter cube. It will be 10 power 15 to 10 power 16 impurities will be diffused into that particular wafer. Means the diffusion concentration will be 10 power 15 per centimeter cube to 10 power 16 per centimeter cube. Means per centimeter cube of wafer, they'll be diffusing 10 power 15 impurities to 10 power 16 impurities. So that's how a purest form of wafer will be converted into P kind of substrate. So this is the first one. That's a P type of substrate. That's step number 2. Step number 2 is oxidation process. Step number 2 is a oxidation process. We all know oxidation. Oxidation is nothing else but it is the burning of any metal in the presence of air in order to produce some oxide. In the same way here, this particular silicon will be subjected to oxidation process in order to get an oxide layer onto the surface of this first step. So see here now, in this diagram, the process goes on like we have one step, one layer over here, then the second one, another layer will be formed upon that particular layer. So on the process goes on. So that's how ultimately at last you'll be having the 3 terminals of the NMOS device, that is source, gate, and drain. So in the oxidation process, due to this oxidation process, first you'll be having your P substrate, and onto this P substrate, with the help of this, with the help of oxidation process, oxide layer will be formed. Oxide layer will be formed. This is SiO2. The thickness of this oxide layer will be 1 micrometer. 1 micrometer is the thickness of this oxide layer, and this oxide layer will be termed as a thick oxide throughout for the next steps. In the next step, this oxide layer will be called as a thick oxide. Why? Because in the process you will be coming across another kind of oxides which are much lesser in size compared to this 1 micrometer. So the next, in the second process, what we do, the previous step substrate will be subjected to oxidation process. In that oxidation process, your SiO2, that's a silicon dioxide, will be formed on the surface of this one, and that will be having a thickness of 1 micrometer. 1 micrometer will be the thickness of this oxide layer. Then the third one, if I go for the third step is called as a photoresist. Step number 3. In this photoresist, photoresist is nothing else but, first I'll talk about what is meant by photoresist. Photoresist is an light sensitive material which is composed of like hydrocarbon polymers and some agents, some chemical agents will be there. So like chemical agents like carcinogens or neurotoxins. So this kind of composition of this kind of materials, we call it as a photoresist. So in total, photoresist is nothing else but it's a light sensitive material. So this light sensitive material will be laid evenly upon this oxide layer. The next process will be, the third layer will be formed upon the oxide layer. Even distribution of this photoresist will be done upon the oxide layer, and even that will be having a thickness of some around 1 micrometer to 2 micrometer. It depends upon the, see whatever the dimensions I am giving over here, it depends upon, it vary from one technology to another technology. It will not be the same from, like if I talk about, if I'm trying to fabricate any kind of end device at 1.2 micrometer, the dimensions will be changing. If I talk about 180 nanometer, the dimensions will be changing. All this dimensions will be changing. Most probably this has been done, this have been defined in your referred book with respect to 180 nanometer only. It has been referred with respect to 180 nanometer. So now, photoresist is nothing else but is a light sensitive material which is composed of some hydrocarbon polymers, and also some organic solvents. So now here we'll be having P substrate will be there. P substrate will be there. Upon this P substrate, anyway we are having this. We have developed oxide. Oxide has been developed. This is SiO2. Then upon to this SiO2, there is another kind of layer has been generated that is called as a photoresist. See, in short, I'll be writing it as PR, photoresist. So this is a photoresist. And one more thing, if I want to tell about this SiO2 acts as an insulator or barrier. It acts as an insulator or barrier. Or for what? For what does it act as an insulator or barrier? It will try to obstruct further diffusing or doping of impurities into the substrate. So SiO2 is mainly used as an insulator or barrier in order to avoid further diffusion of impurities into the substrate. So photoresist is nothing else but it's a layer which is formed on the SiO2 of the thickness 1 micrometer to 2 micrometer, which is nothing else but it's a light sensitive material which is composed of hydrocarbon polymers and also some organic solvents. Organic solvents examples can be like carcinogens and neurotoxins. Then the step number 4. Step number 4 is UV exposure. UV exposure. Here UV exposure means ultraviolet exposure. Ultraviolet exposure. Why do we need to make this ultraviolet exposure? Ultraviolet exposure is a, I can tell simply it's a photolithography process where the patterning of this layers will be done. Patterning means I've been using the word patterning right from the starting of this fabrication. Patterning means we are trying to harden the surface. We are trying to harden the surface of the layers. That hardening process we call it as a patterning here. So now ultraviolet rays, ultraviolet light will be used in order to pattern the layers which are being used over here. So now same p-type substrate we have here down, which is of 1 micrometer thickness. Then upon that one, we have SiO2. SiO2. And on the SiO2, we are having, we have processed photoresist. PR. Then here we'll be using some mask. Mask is nothing else but we'll be using a glass kind of material. Why do we use this mask? Because wherever I want my three terminals, like source, drain, and a gate, wherever I want to form the three terminals, there I'll try to use a thick kind of glass or mask so that the area below that mask will not be affected due to this UV exposure. If it is not affected, means that area will be softer in nature, and the area which is affected to the UV exposure will be hard in nature. So if whichever is softer in nature, that can be easily extracted, or which can be easily etched off in order to develop that three terminals, source, drain, and gate terminals. So now I want to mask, if I want a source and drain terminals are to be produced over here or developed over here, that one I'll make it as a thick glass. I'll be using a thick mask. Thick mask will be used over here, and from top we'll be having the UV rays. These are UV rays. So now, wherever this glass, this is nothing else but it's a mask. It's a mask. It's a mask or a glass kind of material has been used. This, wherever you find this darkened surface is a thicker glass or thicker mask, and the undarkened surface is a lighter glass or lighter mask. So now the area which is below this one will be soft in nature, and the area which is below the lighter a light kind of a glass, it will become hard in nature. So which has patterned, that hardening is nothing else but patterning. Which has been patterned, we cannot etch it very easily, but which is unpatterned, which is softer in nature, we can easily etch it off. We can remove this layers and we can form the source and drain terminals in that particular area. I'll give, kindly note it down. I'll give you two minutes of time. Please kindly note it down and respond to me once it has been done.
Excuse me, sir.
Yeah, please talk to me.
Sir, in the step 1, you have wrote about 10 power 15 to 10 power 16, sir. Yeah. What those values indicates?
Could you please come again? Could you talk louder?
In that step, what those values indicates?
These values are nothing else but the ion concentration, impurities concentration.
Okay.
These are the ion or impurity concentration.
Okay. Thank you, sir.
Kindly note it down. Once if it has been done, please let me know.
Completed.
Yes, sir. Done.
Yes, sir.
Is it done now? Okay, fine. Okay, next step is window formation. Step number 5. Window formation. So window formation is nothing else but it's a process. See here in the previous step, in this fourth step, we have done the masking with the thick glass. Thick glass indicates that the UV rays should not affect the lower surface of that particular glass. So now here, wherever it is not affected, wherever the region of the substrate is softer, you'll try to etch it off by the process, by two different processes, other like chemical etching is been done, also dry etching is been done. In the chemical etching, they'll be using like hydrofluoric acid will be used, and in the dry etching some plasma method will be used in order to etch off this particular layers. So now in the window formation, after that window formation has been done, I'm drawing the diagram of after that etching is been done, after that particular etching has been done. If it has been done, after etching has been done, our substrate looks like this. This is PR, and this one is SiO2. 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 So the see here, you can see that region which was in the middle. It was in the fourth step. The region which was in the middle is been now completely etched off. It is nothing else but it is removed on up to the surface of the P substrate. Up to the surface of P substrate, that particular layers will be removed. Once if the layers have been removed, we can easily form the two different kinds of terminals here. Okay, first we'll be forming the two, and then the later third one will be coming into picture. So now this etching has been done chemically. Chemical kind of etching is there. Other one is called as a dry etching. Dry etching is there. So in chemical etching, they use hydrofluoric acid, and here in dry etching they use plasma method. Plasma method. So this is called as this formation of this kind of structure we call as a window formation. Window formation. The next one, thin oxide formation. The step number 6 will be thin oxide formation. Thin oxide formation. So now here, in this particular process, onto this layer, onto this particular layers of Pi and also SiO2, another kind of oxide will be layered by using again the same process like create, define, and photolithography process. They'll form another layer of SiO2, but the size of that particular layer will be of only 0.1 mm. 0.1 mm. That's why we call it as a thin oxide. That's why it is called as a thin oxide. Once the window formation has been done, the next one will be 0.1 dimensional part of the oxide layer will be formed. So I'm drawing the diagram now. So completely, this one will be a combination of this SiO2 and the top one will be tin oxide. The top one is nothing else but tin oxide. So now here, in this process of laying this SiO2 thin layer, before laying this thin SiO2, the PR will be removed. The PR also will be completely will be etched off. Once the PR has been etched off, then the thin oxide will be formed. So this is nothing else but the thick oxide. Thick oxide means thick SiO2. The dimensions are like 1 micrometer, and top of that one is a thin oxide, and it is of only 0.1 mm. It's a thin oxide. Since it is a thin oxide is laid upon this thick oxide, we call this method as also thin. Excuse me. We call it as also, this method name can also be named as Tynox formation. It is Tynox formation. It is also, since a thin oxide is being laid upon this SiO2, thick SiO2, it is also called as a Tynox formation. And the dimensions of this Tynox will be 0.1 mm. 0.1 mm. So this is regarding how a thin oxide has been formed upon the upon this window. Once the window has been formed, later upon that one, the thin oxide has been laid. And before laying of this thin oxide, before laying of this thin oxide, the PR, that is the photoresist, will be completely removed, and therefore this entire thing will act as a thick oxide. That's why I have drawn the two layers of SiO2, which indicates a thick one, and the thin one indicates a smaller part of the SiO2. Okay.
Sir.
So then next step.
Sir, what is the use of PR then?
Excuse me.
All the PR is removed, then what is the use of that, sir?
See, a PR is like a PR, SiO2 and etching. It will be continuously, it will be happening. It's only like a polymers will be diffused into that one. It's on the diffusion process already taken place. So now whatever is the layer is there, the layer will be removed. It's like it becomes like an unwanted layer. The material of PR will be completely diffused into that substrate. After that only, see why I'm telling about diffusing, because this entire patterning will be done like this wafer will be taken and it will be kept into an oven at 900 to 1200 degrees Celsius. You can imagine to what extent that particular wafer will be subjected to that amount of temperature. So whenever it is subjected to that huge amount of temperature, the patterning will be done, and the diffusing of this, all the properties of that particular layers will be done into the substrate. So that's why now the PR becomes unwanted layer.
Sir,
it will be etched off.
sir,
Yeah,
in order to lay the mask only, we'll keep the photoresist layer, sir, because photoresist layer is applicable for UV rays transmission. In order to perform masking only, we will lay the PR, na, sir.
First of all, what is masking? Masking
Masking
is
is
nothing else but it's an electronic data. It's an electronic data, ma'am. It's like electronic data means I'm talking about these dimensions. It's a specifications about the geometry. Masking is nothing else but it's a specifications of geometry. So once the importance of PR has been diffused into the substrate, it will be etched off. It will be removed. So continuously, PR will be laid, PR will be etched off in this entire process. In the entire process of this fabrication. So next one. Let me go for the next step. It's a gate formation. Step number 7. gate formation. So now here in the gate formation for forming a gate, they'll be using a material called polysilicon. Polysilicon is nothing else but it's a crystalline form of the silicon. The crystalline form of the silicon will be used in order to form the gate, and that particular gate will be formed in the center part of this one, in the center part of this window, and that has been done by using a polysilicon material. In this in the seventh step, this will be the seventh step, where you can even see in the seventh step, like again the PR coating will be done, again PR coating has been done, again the silicon, thick silicon will be laid. So that's how this layer has been formed here below this gate terminal. So a PR coating and thick oxide layer formation, all this will be a continuous process. It will be a repetition process. Wherever a new layer has to be masked, wherever a new layer has to be patterned. So this will be the seventh step. This gate terminal has been formed by using a material called polysilicon. Polysilicon is nothing else but it's a crystalline form of the silicon. It's a crystalline form of silicon. So now here, this is thick SiO2 and this is the pinox. You can note it on all these 7 steps. Next, we'll see the 8th step where source and drain will be formed. Kindly please let me know once if it is done. Is it completed? So next process will be source and drain formation. See here, just now I told that below this gate terminal, that's below the polysilicon material, again you will be having the combination of the Stynox and SiO2 will be there. The main use of this Stynox or SiO2 below the source and below this gate material is that it will try to protect this particular area from diffusing of the impurities which are mainly used for formation of source and drain material. So underlining this particular gate terminal, there will be this Stynox and silicon SiO2 layers will be there, and this process of showing some kind of resistance to the impurities used to form the source and drain terminal is called as an self-aligning. Self-aligning is a very important word in the fabrication. Self-aligning is nothing else but it's a process where the SiO2 and the thin oxide and the thick oxide are being used in order to protect that region of the gate terminal from getting diffused by the impurities which have been used for source and drain terminal. Now let us see for the source and drain formation. In the source and drain formation, the source and drain formations are mainly done by the impurities of N-type impurities have been used. N-type of impurities have been used like phosphorus or pH3. Phosphine, these gases have been used for diffusing the N-type of impurities, and this diffusion of N-type of impurities will be done again at the very high temperature like 900 degrees Celsius to 1200 degrees Celsius. Then at that particular temperature, this gas will be passed through this particular substrate layer so that the N-type of impurities are being diffused at the area which is on the either sides of this gate terminal. So now here in the region here and here, N-type of impurities have been used, and these two regions will be called as a source and drain terminals of a MOSFET.
Excuse me, sir.
Excuse me, just a minute now.
Sir, the screen is looking somewhat blur.
Is it okay now?
No, sir.
Because I don't have any kind of problem from my side. Why? Because I'm on Wi-Fi, which is of nearly 50 Mbps of speed. Kindly check your data once. Check your internet signals.
I'm also using it. No, now it is okay, sir.
I don't know whether it will be visible to you or not, so that's why I'm not writing in the bracket. It is N plus impurities are being diffused over there with the help of, and this will be the gate terminal, which acts as a gate terminal in the next process steps. And so this is now here the area where either side of the gate terminal will be used to diffuse N kind of impurities with the help of phosphorus or phosphine gas. That particular gas will be passed whenever this particular P substrate is subjected to 900 to 1200 degree Celsius. So let us see now. Let us see what will be the maximum penetration. To what level this particular impurities can penetrate. The maximum penetration level for this impurities will be 3 micrometer to 30 micrometer. 3 micrometer will be 3 micrometer to 30 micrometer. So now the maximum penetration of this particular impurities will happen from 3 micrometer to 30 micrometer. 30 micrometer. So now this is the penetration. Maximum penetration level. The maximum penetration level happens from 3 micrometer to 30 micrometer in this particular substrate, and the speed at which this particular impurities are being diffused into the substrate. That's nothing else but the rate at which the impurities are being diffused into the substrate will be like 1 micrometer per hour. The rate of penetration. The rate of impurity, you can name it as the rate of impurity diffusion. The rate of impurity diffusion will be like 1 micrometer per hour. The rate of impurity diffusion will be 1 micrometer per hour, and the maximum penetration in this particular area of substrate, the impurities will be penetrated to maximum level of 3 micrometer to 30 micrometer. So these are the first 8 steps, source, and this is how a source and drain will be formed. This is how a source and drain will be formed. by penetration or by diffusing n type of impurities after subjecting the particular substrate to 900 degrees Celsius to 1200 degree Celsius. And the material which is used here for n type of impurities will be phosphorus or pH3, phosphine gas will be used for diffusing for n type of impurities. So please note it down. I'm erasing this first two, fifth and sixth steps.
Sir, sir,
Yeah, please tell me.
sir, అక్కడ n ప్లస్ అని ఎందుకు ఇచ్చింది సార్? n టైప్ అని రాయొచ్చు కదా.
కొద్దిగా గట్టి మాట్లాడగలుగుతాం. Could you please talk louder?
n ప్లస్ అని రాసిల్లు కదా సార్.
N plus.
n ప్లస్ కి n కి తేడా ఏంటి సార్?
N plus అంటే it's a impurity, highly concentrated impurities.
హై కాన్సంట్రేషన్ అంటే ఎంత ఉంటుంది సార్ రేంజ్?
అంటే ఆ రీజియన్ లోపల in that particular region, see what is this entire region here? What is this entire region? It's a P type of substrate. A P type of substrate lopala, after etching process, you will be diffusing high doping concentration. It will be highly doped. It is called as a highly doped area. So that's why the highly doped area will be denoted by plus naught. And what kind of impurities are used here? N type of impurities. That's the main meaning of indicating it as N plus. It indicates that it's a high doped area with N type of impurities. The next one is contact cuts. Next step, it is ninth step. Contact cuts is nothing else but it's a small part in this fabrication. Contact cuts is like wherever we need. See again, after this process of fabrication, after this process of source and drain, again other layers will be laid, again etching process, continuous process will be going on. Then in that after that continuous process, wherever we want our terminals, wherever we want our metal terminals to be connected, and then you all know that this MOSFET will be having 3 terminals, and that has to be in terms of a metal, so that it can pass the current through that to that particular device. So now wherever you make this metal connections, that area has to be completely etched off. It has to be completely etched off. So you should make it as free for laying metal in that particular area. The removing of that other layers in order to create a space for metal layer, any kind of metal, like in this one we use like copper, aluminum will be used because they are very much good conductors. So in order for laying of the copper and aluminum, we are supposed to create a space or area. That process of creating or etching process is called as contact cuts. It's like the smallest area. Again, on this process, different layers will be laid, and in the small region, I'll be etching off. That small region will be a place where my wires will be coming out. In other words, if I want to call, I can call it the wires. I need to pull it from that particular area. See, this small regions, this small area, I can call it as a, excuse me, I am not drawing a small. This is called as a contact cut, the area where I left the space. So these are the other kind of masks. See, here the masking of this fabrication, it depends from manufacturer to manufacturer. Nearly like in whole, if you want to get an integrated circuit physically, there will be like nearly more than 200 steps will be there. But basically, these are the basic steps which are used. So apart from that one, depending upon the technology, depending upon what kind of material they have used. Why? Because we have different kind of materials, different kind of technologies. Gallium arsenic technology is there. Again, different kind of technologies are coming up. So depending upon different technologies, different materials will be used, and depending upon these characteristics, the mask layers also will increase. So as of now, they have calculated to some extent of more than 200 steps are being used by different manufacturers in order to develop one integrated circuit. So that's why this indicates what are the layers I have drawn. These are different masks which have been drawn, and after that one, etching process has been done in this area where I want my terminals to come out of this particular device. So these terminals will act as a gate, source, and drain terminals. Then last one. The last one is the 10th one. It is called as a metallization. What are the steps I'm drawing? I'm writing here or drawing here are the basic steps. Without these steps, we cannot manufacture integrated circuits. Apart from that one, in between this basic 10 steps, there will be many steps like laying of the layers and etching process, photoresist, all this will be happening. So last one, metallization. Metallization is nothing else but it's a process of laying the metal layer, especially in the area where the contact cuts are being developed, so that these metal layers in the contact cuts will act as the three terminals of the MOSFET for further connections, for further electrical connections. And after this one, completely, your metal layer will be laid off. This is how the three layers comes out.
Sir, screen is not visible, sir.
The screen sharing has been off.
Your video is turned off, sir.
Yeah. This is how the metal will be laid completely upon this one, and wherever I want that metals as a gate, source, and drain, that will be pulled up, and this will act as a source, gate, and drain terminals. And the metal which is used here is aluminum or copper. Aluminum or copper. And the thickness of this metal will be like 1 micrometer thickness will be used. 1 micrometer thickness of metal is used in order to do this metallization. Please note it down. So once after this metallization has been done, once after the completion of metallization, next will be the passivation method. Passivation method is nothing else but they'll cover this entire IC with some passivation materials like which acts as a barriers for external world, so that any kind of harmness should not take place to the integrated circuit, which can even degrade the functionality of a device. It can be of any kind of device, pMOSFET or NMOSFET. So now here in this particular class we have studied about in this particular class we have studied about NMOS fabrication, where it has got 10 basic steps.
Sir.
Yeah, please tell me.
Third layer ఏంటి సార్ అది మెటలైజేషన్ లో
Huh?
థర్డ్ లేయర్
This is metal.
సార్ మొత్తం
This
మెటల్ అయితే
top one is a metal.
షార్ట్ సర్క్యూట్ అవుతుంది కదా సార్
Yeah.
మొత్తం షార్ట్ అవుతుంది కదా సార్ మొత్తం మెటల్ అయితే
Here, first is metallization only. I have drawn here only to show you that one. After that, again, etching process cheshaka, this 3 layers will be pulled up. Have understood or not?
ఓకే
Completely metal will be laid upon this integrated circuit. Completely metal. Sorry, excuse me. Metal will be laid upon this entire device. Then after that, etching process will be done. After that etching process, the interconnections will be pulled up. These are the 3 interconnections. In order to make you understand, I have drawn blue lines.
అంటే మళ్ళీ ఎచ్చింగ్ చేసి ఎక్కడైతే కావాలో అక్కడే ఉంచి
So
మిగతా
now
అంతా
this NMOS
తీసేస్తారు
fabrication, we have studied about 10 different steps. Yeah.
ఓకే సార్
After that, passivation will be done.
ఓకే
Like different chemical techniques are there to passivate the integrated circuit, to protect the integrated circuit from any kind of harmness from the environment. So in this particular class, we have studied about NMOS fabrication, which has got nearly 10 steps. Like first one goes with substrate formation, second one will be oxidation, third one will be PR, that's a photoresist, fourth one will be UV ray exposure, fifth one will be Tynox. After that, after UV ray it will be window formation. Then after that, Tynox will be there. Once the Tynox formation has been done, then will be the gate formation, source and drain formation. Next will be source and drain formation. After that, contact cuts, and last one will be the metallization process. So this is how the entire process of fabrication has been done in order to get a physical NMOS device. So in the next class, we'll study about the pMOS fabrication. All the steps will be same except these 3.